Okay, is everyone ready? Okay, so welcome everyone to this workshop. This workshop of the collaboratory analysis of electronic health records. I'm Ákos Rudas. I'm a postdoc at the Department of Computational Medicine. I collaborate with physicians and clinical staff to find data science-based solutions to their problems and questions. I also work with numerous data sets managed by UCLA. And in regards to one of these data sets, I would like to share a couple of numbers. Over 6.4 million patient records, over 129 million lab results, over 207 million patient encounters, and over 480 million recorded diagnosis codes. This is what's stored inside the DDR, the Discovery and Data Repository, which is a de-identified data set, which UCLA has accumulated over the last couple of years. And it's up for the grabs for any researcher who can use this information and who also know how to use it. So with that in mind, my intention is that by the end of this course, you will know what data is available in this database, how this data is stored, how you can write queries to retrieve this data as close to your intended data set as possible, and what are some best practices, how to avoid some pitfalls which can happen when dealing with this database. The way I'm planning this course is first we are going to just make sure everyone has their environment set up. That usually takes some time, but I think this year it's going to be easier. And then we are going to touch new concepts, and then we are going to solve some exercises with those new concepts. Then we're going to go to new concepts and solve more exciting exercises. And this should be the plan until Friday. First, we are going to query entire tables from the database. Then we are going to limit our queries to certain columns and rows. Then we are going to write queries which will operate on multiple different tables, pulling different sorts of data together. We are going to form groups in the data set, and we are going to look at some aggregation strategies. We are going to write more complex queries with more complex structures. And I think by the end of this course, we are going to get to discussing real-world complex queries. Since we are going to use the DDR as an example for all of the exercises, you will all get very familiar with the DDR by the end of this course. This is good. No questions so far. Awesome. At this point, I'm going to stop the recording. Okay, so let's get into the SQL basics. SQL stands for Structured Query Language. So what we have here, what DDR is, and what SQL language is designed for are called relational databases. And relational databases contain relations. So what are relations? Here we see 3 examples of a relation. What is the relationship between this 5 and 6? Anyone? Exactly, 5 is less than 6. We can say the same relationship about 3 and 9. 3 is smaller than 9, and -2 is smaller or less than 0. So since we have relational databases, we should be able to store this in a database. But how do we do that? This is what we would normally call a table. We can also call this a relation, and I will use these 2 words interchangeably. So relations are tables, tables are relations, in this context at least. This table, this relation is called smaller, and it describes a smaller relationship between 2 numbers, x and y. So every row of this table contains a pair where x is smaller than y. In the first row, 5 is x, y equals 6, and so 5 is smaller than 6. So this is one kind of relationship. Let's talk about a different kind of relationship. Which one is the other one which never sinks? Friendship. My daughter knows that. She told me that. So the next relationship is Anne is friends with Michael, and Anne is friends with Lucy. Again, we see two examples of relationship. So how do we store it in a database? We store it in a table or relation. In this relation, the name of the relation is friends, and we have two columns, friend 1 and friend 2. And every row represents a pair of friends. So let's go forward with this table. This is a database, so let's put some more data into those sentences which we would like to store in the relational database. Let's say Anne Smith is friends with Michael Jones, and Anne Smith is friends with Lucy Green. So there we go. We can easily store this extra information in this table. Another attribute, let's say, of a person would be their date of birth. So now we not only store their names, we also have information about their dates of birth. However, I don't really like this way. Does anyone have any issues with this representation of the data? Do you see any issues with it? Yes, so her name is spelled out multiple times. Her date of birth is spelled out multiple times. What do you want to mention? We will get to that. And very good. And we will start with this. That is also true. Yes, you guys are great. You already found most of the issues. So the first one, what you said, Anne Smith is written down multiple times, so is her date of birth. So the first issue with this way of storing the data is redundancy. There's no need to store these many times. So what happens, let's say, if we learn that Anne Smith's birthday was not recorded properly? Maybe that was a typo, and her birthday is actually April 16, 1986. So how do we solve it? What do we do? Any ideas how to fix it in this table? We would need to modify every record which contains Anne Smith's birthday. Now, it means that in this case, we have to modify it 2 times. If Anne has, let's say, 18 friends, it means that we have to modify it 18 times. So it's very inefficient. Inefficient in a computational sense, and also inefficient in a storage sense, because we are storing all these fields. Okay, so what if Anne stops being friends with Lucy? And we remove the second row from this table. Will we still know when Anne Smith's birthday is? Yeah, we know. Do we know when Lucy's birthday is? No. So it doesn't really make sense, right? That a person stops being friends with other people in the data set and we lose their date of birth. So this is also an inconsistent way of storing our data. So what would be the solution for this? Any ideas? Precisely. So we will have 2 tables now. We will have one which is called a person table, and there we will store the people's information such as last name, first name, or date of birth. And we have another table, another relation, which actually describes relationships between the people, the persons. And there we store that Anne is friends with Michael, Anne is friends with Lucy. But what happens if, let's say, Michael becomes friends with Anne Chang? What happens then? And we will have another row called Anne and Michael. How will we solve that? Let's say it's not even Anne Chang. Let's say it's another Anne Smith. Yes, we will add a special field to the first table, and we will call that an ID field. We call that a unique identifier, and its purpose is that it identifies one record in that table uniquely. So you will never find two rows with the same ID. And if it's true, if that holds, then this ID field is considered to be a unique identifier. So there we have our answer, how to store these friendships in a consistent way. We will use the people's IDs to describe their relationships. And you can clearly see that now if we remove the second row from the friends table, we will still have Lucy's birthday stored in the person table. So far, so good. So again, one table contains properties of an entity, and another one contains a relationship between entities. And can relationships have properties too? What do you think? What property could this friendship have? Could be. My example would be since. So like, when did they start being friends? Right. So just to go over the terms we've touched so far, we will use table and relation interchangeably. This table or relation is called patients. Its header is the ID, last name, first name, date of birth, and sex. We also call that the schema of the relation. One row is one entity. Here, the entities in this table are people, patients. Columns represent attributes of the entities. So we will use column and attribute interchangeably as well. And we will use the term primary key for the key field, which we use as a primary identifier. Again, primary identifier will refer to one single row without ambiguity. And let's just talk a few sentences about data types, which you will encounter in this database. So one is numeric. It can be integers. It can be floating point numbers. We have varchars, which is short for variable character or variable length character. So this is a string. These are strings. We have the Boolean data type, which is true or false. Actually, to give you an example, in many databases for efficiency, instead of using a sex column, they would either use a male or female column, and they will use true or false. And so if the column is called female and it's true, it means that the patient is female. And if it's false, it means the patient is male. Here, as you can see, we basically use varchars or one long varchars, which we can call a character. And we also have a special data type called null. And null is kind of different than the other ones. It's not a real value. It's indicative of a missing value. So why can data be missing? So the first example is when the data is physically missing. So maybe a physician input some data based on some chart, and then the patient did not complete one of the fields. So that will be filled with a null, which doesn't say that it's zero. It doesn't mean it's an empty string. It means it's null, it's missing. If you try to equate it to anything, if you want to check whether this, maybe the age is missing, and you want to check whether this person is 20 years old or not, you will not get yes or no, you will get an unknown. Just think about this, that in databases, you can have truths, falses, and unknowns. This is something to look out for. Another appropriate occurrence of none is when the data is simply just not applicable. Let's say patient have a field called spouse ID. If they don't have a spouse, it's going to be null. Not because the data is really missing, but because it's not applicable, because the person is not married. So these are two, I would say probably the two most frequent occurrences of nons or nulls. So far, so good. Any questions? Okay, then. We're going to move on to a very simple and intuitive slide, just to give you an idea of the data set. Like, almost no explanation is needed. This is the organization of the DDR database. You can return this, and I will also send this out in an email so that you can use this as a reference when you're working with tables. I'm not sure if we actually need it, but sometimes it's good to look at it. If you remember previously, I mentioned that you will have fact and dimension tables. These are the two big groups of tables you will have. And you also remember that when we worked with the friendship tables, we had one table for patients and one for the relationships. So the idea here is kind of the same. We have the fact and the dimension tables. The fact tables, basically, I think the best way to think about it is that they represent events. Did the patient have an encounter with the medical system? That's an event. Did the physician prescribe some medication? The prescription is an event. Was the person hospitalized? It's an event. These are events. And then we have the dimension tables, which contain the properties of the participants of these events. So maybe a patient was hospitalized. Then we had a patient in this. We had a hospital in this, right, a department. And we probably had a nurse or a physician who did the checkup on the person. So these are three entities, and they will have their data detailed in a dimension table. Consider this encounter entity. This table contains encounter information. An encounter is when a patient touches the UCLA Health medical system. This is one encounter. It can be a personal visit. It can be a telehealth visit. And so who's going to participate in that? There's going to be a patient, obviously. And then we will be able to find data regarding the patient in the patient in table. There will be a hospital and a department involved. So where will we find the information about that department? We find this in the department in table. Okay, there will be a provider for the patient. So where will we find that provider? In the provider in table. Was there a medication prescribed? Cool, we will find the medication details in the, who can guess? The medication table. Thank you. Okay, so we will sometimes maybe return to this slide or just keep it for reference. Is this idea clear? So we have basically facts, and then we have dimensions. Okay. So let's talk about our very first SQL query, the select star statement. So let's try to read it as a real sentence. Select star from relation. Star in this case is a placeholder for all of the columns which are available in a specific relation. Let's look at an example. Let's say we're going to say select star from patients. This will be the result. You remember this patients table? So here we selected all the columns. We didn't say select ID, select last name, just select star. So we selected the entire table. Whenever you say select star from table, it means that you are querying the entire table. So this is the select star statement. What if we want to be more selective in what data we really need? Instead of the star, we can provide one field name or a list of field names, list of attributes or column names. You can use any of these terms from a relation. To see it in an example, we can select the last name and the first name from patients. Okay, so in this case, we select the last name and the first name columns, and they will be part of the output query. A good way of thinking about this is that SQL statements operate on relations, and then the output of SQL queries are also relations. If you think about it, this is the entire patients table with 5 columns. This is the output of our select last name and first name statement. It has 2 columns, but all the rows. Make sense? So we arrived to our first set of exercises, and let me stop recording now. Okay, so now that we know how to query entire tables with all its columns, all its rows, and not all its columns, but specifically just those of interest, let's learn how we can select specific rows. Well, we sort of learned one way of doing that, limiting the output with the top something keywords. But let's do it with a more exciting way, with an actual condition which the row has to satisfy. So how does it work? Let's say that we would like to have all the rows with patients who are females. So we continue the query structure which we already started. We say select star from patients where, this is the where keyword, and the where clause contains a condition. The condition is sex equals F. So the way it works is the from patients part gets evaluated and it loads the table. Then the interpreter sees where sex equals F. So it will consider the sex column and will only keep those rows which satisfy this condition, where the sex column contains a letter F. Okay? These are the two rows which satisfy this condition. And so these will form the resulting query outputs as such. Okay, so again, we had a query operating on a relation and resulting in a relation. So far, so good. We can also do the inverse operation in a sense. We can select all the rows from the patient's relation where it's not true that the sex equals F. In this case, we will have a single row satisfying this condition. The result will be a relation with a single row. It is still a relation, though. Any questions on this? So you can see some of the new elements which we are using. We are using this more classical equating two things to one another. We are using this sex as if it was a variable, and we are using F as a literal. So we are equating a variable to a literal, if you want to hear this from the programmer's aspect. So we just arrived to the second list of exercises. So let's move to using the select and the where clauses together. You kind of already saw an example of this, but let's just go into a little bit more details. So let's say that we would like to query the last and the first name of patients who are females. So the way to address it is, and I would like to show you on these slides how basically to think about the evaluation of these queries. So first, we are selecting only the rows which satisfy this condition, that sex equals F. So we have two such rows. I color them red. And then we are only interested in two columns of this, the last name and the first name. I try to color them blue, and then you can kind of see how the purple one are the data fields which we will actually be expecting in the output query. And this is exactly how it works. But we just saw an example of this. So let's go to exercise 3, when you will actually need to specify the column and the where clause as well. So you will be limiting your output also in the number of rows, but also in the number of columns. So the 3 examples here, and these are going to be, so at this point, we are not going to join tables, but you will need to find data in different tables. So not just the encounter one. So the first one says, list the heights and weights of patients who spent at least a week in the ICU. So when you see something like this, the first step is to identify what tables do you actually need. So you've seen the encounter tables, and you know that it contains many information, for example, patient age and time spent in the ICU. But here I ask about the heights and the weights of the patients. So this is something you have not seen yet. So it might be in the encounter fact table, it might be in another table. So the first step is to look at the columns and figure out where will you find this data. Because before writing a query, you will need to know which table you are writing the query for. So this will be 3.1. 3.2 is select an encounter. And here, what I mean is just select a random encounter. Just look into the table, query the first couple of thousand rows, look down and find one, and then try to look up the patient ID. So try to look up the patient who is part of this encounter. Let's try to find information on the patient. Try to look into the tables and see which one contains this information. And the same goes for the discharge disposition code, which is a code for how the patient was discharged from the visit, from the encounter. And the same goes for department ID. And let me tell you that the discharge disposition code will be the most difficult. So start with the patient ID and then the department ID. And then we're going to go into the nitty-gritty of the discharge disposition code and into exercise 3.3. It says list all possible discharge dispositions. And I put some hints here, so you can give it a try, but we are going to spend time on it together because that will be a more difficult concept, how data is organized in that specific table, in the category table. So far, I told you how to think about these data sets as relations, basically a set of tables. And in the tables, you have rows and columns, they have orders. Now I want you to, although remember this, but be ready to think about this whole thing completely differently. Let's consider that all the relations are actually sets in the mathematical sense. So if you think about tables as sets, so basically the rows have no ordering. They are basically just floating in the table. Then you can consider this as a set of entities. And if you have a set, that means that set operations can be interpreted on them. That means that if you write a query and another one, or you just have two tables, you can form the union of the two, the multi-union, the intersect, or the difference between the two sets. Okay. Actually, an even better way to think about relations is not as sets, but more like multi-sets, which means that one element can occur multiple times in the same set. Okay, so like this would be, this in a mathematical sense, this would be a set. Oh, sorry, that would be a B. That's a B, C, D. In a mathematical sense, that's a set. If I put another A, then it's basically it should be the same as A, B, C, D, right? This is the classical sense of sets. In SQL, we think about relations as multi-sets, which means that the same row can occur several times in the same table. And we are going to experiment with this. Okay, so just that everybody understands, union of two sets means that the union will contain all the elements contained in either one of the sets. Okay, so if we have AB and CD, then the union will contain ABCD. Union all in the multi-set sense means that if we have AB here and we have AC here, the union all will have A, B, C. Okay, A and B from this side, A and C from this side. The A will occur 2 times in the resulting set. We will have the intersect, AB, AC. We will have A in the intersection. And for except, if we have AB from your side, now the order matters. So I have AB and I have AC. So if I take the difference, if I take AB minus AC, what I will be left with is B, because this set had A and C, and we removed it from this one. It did have A, so it was removed. It did not have C, so it didn't affect it. What was left in this was the B. So far, so good. Okay, so from now on, tables and relations are also multi-sets. This is my agenda to make you as confused as possible by the end of the day. So let's see some examples with our toy tables. So let's say we have one query saying select last name, first name from patients. You will see this T1 as the output table. And then I'm doing another query. It says select last name, first name from patients where sex equals F. So we are just selecting the females. So now we have T1 and we have T2. These will be our two sets for the examples. Okay, T1 has all the patients, T2 has only Anne and Lucy. So now we can interpret the intersection of the two sets, right? Anne and Lucy will be in the intersection of the two sets. Okay, so we're intersecting all the patients with only the female patients. So the resulting set will be only the female patients. The keyword which I use here is intersect. These set operations are a good example of when something is usually different in, between SQL languages. Sometimes it's intersect, in others it's intersection, for example. So anyway, I use the intersect keyword, and on both sides, I have a relation. These are queries, but as you see, they are not queries on their own because I am continuing the query, so I put them in brackets. And so they will be handled as basically temporary tables in the memory of the computer. So the first one will be created, the second one will be created, and the intersection of the two will be generated. Same goes with the union. We can take the union of the two sets. In this example, it's just T1. I'm using the union keyword. And if I want to remove one from the other, I use except. In Oracle SQL, it's actually minus. The keyword is minus. Here it's except. I'm just saying this because if in the future you are working with a database, you write a query, but that's not that database, not the UCLA's DDR, but a different one with a different SQL version, and you wonder why do you get an error for the except, that might be the issue. Okay, so let's jump into our last set of exercises for today. So one important note for these set operations. So as in mathematics, you can only have one data type in a set. So you can't have numbers and strings in the same set. Similar here, but what will determine the data type? So let's say that we talk about these two queries which we just wrote, where we selected the patient ID and the encounter ID. What's the data type? Any guess is good. Or? So right, the patient ID is numeric. The encounter ID is numeric. But we're not dealing with the patient ID or the encounter ID. We are querying pairs, right? So here the data type is specifically a tuple where the first one is numeric and called patient ID. The second one is numeric called encounter ID. If the data type doesn't match or the column name doesn't match, the SQL server will have no way of determining whether they have the same data type. So you will get an error because you cannot create sets from sets with differing data types, which means that when you look at relations as sets and you want to perform set operations, every time you will need to make sure that the data types and the schema, the header of the table, is exactly the same, okay? They both need to be the same. If one is patient ID, encounter ID, patient age, because you wanted to check the patient age, but maybe in the other one you didn't want to check it because you knew already it will be correct and it will be just patient ID, encounter ID, it will not gonna work. This tuple will have, this will be a tuple, this will be a triple, so you will not be able to create a set. But then you can write a query which will only which will project on that two fields, which you need the patient ID and the encounter ID. So you can just say select patient ID and encounter ID and just basically leave the patient age out, and then they will match. Exactly. Exactly. So you can have two different tables with different schemas, because you might want to create a set based on just a couple of attributes. So then you create one query for this one and one query for this one. The resulting queries should have the same schema, and then you can perform set operations on the two resulting sets. Okay. So with that, the first day has concluded. And tomorrow we are going to deep dive into joining several different tables into one query so that we can combine data from different places. So stay tuned. Thanks for joining today.